So this is the third part of the series, What Derivatives Tell Us About the Shape of a Graph. In this short video, we'll illustrate an example of how to use the first and the second derivatives in order to describe the shape of a graph of a function. Let's start with the functions f of t equals to 3t to the fourth minus 8 times t cubed plus 12. Keep in mind that this is a polynomial function, so its domain is going to be all real numbers. Well, the first question is, on what intervals is the function f increasing or decreasing? To answer this question, we first need to find critical point of the functions by finding the first derivative and set it equal to 0, and then you can solve for t to get t equal to 0 and t equals to 2. So the first derivative function is also a polynomial function, which means that its domain is all real numbers, which leads to t equal to 0 and 2 are the only critical values or critical points. Now we're gonna make a table of values by starting with the domain of the functions, and you add 2 critical points and you pick test point in each of the interval. The next step is evaluate these test points using the first derivative function. F prime of -1 is -36, which is less than 0, which means the function is decreasing on this interval. Go to f prime of 1 is also a negative value, which means the function is decreasing on this interval. Go to f of 3. The first derivative of f of 3 is 108, which is a positive value, which means the function is increasing on this interval. So using this table, we can make conclusions about the function f of t is decreasing on -infinity to 2. So we combine the two intervals from -infinity to 0, from 0 to 2, into just -infinity to 2. And f of t is decreasing on 2 to positive infinity. Alright. Now the next question is, can you use the first derivative test to locate local maximum and or local minimum if there's any? In order to do this, we're going to look at the table again to see we look at the critical point to see if there's any changes in the behavior of the functions. So we see that function f of t changes from decreasing to increasing at t equals to 2, which means there's a local minimum at t equals to 2, right? And you can find the local minimum value, which is the y value of the local minimum, by plugging 2 into the function to get -4 as the local minimum point of a function. How about when t equals to 0? When t equals 0, the function doesn't change the behavior at all. It's decreasing and decreasing after 0, so which means t equals 0 is neither a local maximum or a local minimum. And the next question is, on what intervals is f, the function, concave up, concave down? For concavity, we need to find inflection points by finding the second derivative of the functions, which is the derivative of the first derivative of the function f of t. Right? And then you set the second derivative equal to 0. You solve for t to get t equal to 0 or t equal to 4th over 3. In order to find out about the concavity of the functions, we again create a table, starting with the domain of the function, include the 2 inflection points, and pick a test point in each of the interval. We use a second derivative function to evaluate each of the test points. Start with f double prime of -1 to be 84, which means it's positive, which means the function is concave up on this interval. Let's go to f double prime of 1/2, which is -15, which is negative, which means the function is concave down on this interval. Let's go with f double prime of 2 is 48 positive, so the function is concave up again on this interval. So by conclusion, you can say that the f of t is concave up on the interval from negative infinity to 0 and from 4/3 to positive infinity, and is concave down on the interval from 0 to 4/3. The next question is, can you use the second derivative test to verify your answers in part B? Remember, in part B, we found that at t equals to 2, there's a local minimum at t equals to 2. T equal to 0 is neither a local maximum or a local minimum. So we know that we found two critical points, 0 and 2. Now we use a second derivative to evaluate these two critical points. If you plug 0 into the second derivative functions, you get 0, which means it's neither positive or negative when the test fails. The second test fails, which means you have to use a first derivative test. And at this point, the first derivative tells you that t equal to 0 is neither a local maximum or a local minimum. How about when t equals to 2, you plug 2 into the second derivative function, you get a positive value, which means at t equals to 2, you have a local minimum. Because 2 is in the concave up interval, because of the second derivative is positive. So if you have a concave up interval, you have a critical point in it, which means that critical point has got to be a local minimum. All right. And again, we just use the second derivative test to verify our answers in part B. In part B, we found 0 is neither local max or local min, and 2 is a local minimum. So we verify our answers. One more thing, we can graph the function to see if our work was correct. In this graph, you can see that there's critical point number 1 at 0, right? And you see that it's neither a local min or local max. And you have another critical point at 2, so it's clearly a local min, and you have an inflection point at 4/3. All right, now it is your turn to try. Given these functions, can you answer these following questions? Try it and have fun.